All right, so I think I'm live now. Can someone confirm if I'm live and if the audio is perfectly clear? I have a feeling there might be some issue with the audio. Yes, you are live. Okay. Is the audio perfectly fine? Yes, Yagnik says yes. Okay. Yes, sir. Dheeraj says yes, sir. Okay, cool. All right, so we're going to be solving educational code forces round 143 today. It was rated for Div-2, and I'll be solving the first four problems, problem A, B, C, and D. Okay, Anshaz says yes. Okay, cool. All right, okay, I actually have couple of people already replied how many questions they were able to solve. Pragnesh says two, Dheeraj says two, Manan says two, Yagnik says two, Ankit says two. I see mostly people were able to solve two problems only today. Okay. Problem C and D are good. C is actually a very good question, I would say. It's actually a very conceptual question which will actually teach you some concepts which are very necessary for competitive programming. So you're actually going to learn a lot with problem C. And I'll actually teach you the basic concept that I use in the problem C today. Okay. Some people were able to solve 3. Maybe they were able to solve D. D was very easy. D is like way too easy. Nitesh says 2 only. Okay, cool. Alright, so how many people do we have right now? Okay, we have 15, around 15 people. Do like the stream, guys. I only see 8 likes. And let's start with the very first problem. I will be solving problem A, B, C, and D today. So let's start. So, problem A. There are two tars consisting of blocks of two color, red and blue. Both tars are represented by strings of character B or R, denoting the order of blocks in them from the bottom to the top, where B corresponds to the blue block and R corresponds to a red block. So basically we have two tars. Both the tars might contain any number of blocks and any color of blocks. Okay, there are two colors, blue and red. Okay, so now the problem says that you can perform the following operation any number of times. Choose a tar with at least two blocks and move its top to the top, move its top block to the top of the other tar. Okay, so let me just. Alright, so if you see what they are actually doing here is they have taken the topmost block and shifted it here so that their new tower becomes this. Okay, that is the operation that you are allowed to do. You can do it from tower 1 to 2 or from tower 2 to 1. Sorry, this was from 2 to 1 and or you can do from 1 to 2 as well. Okay, cool. Alright, the pair of tower is beautiful if no pair of touching blocks has the same color, i.e. no red block stand on the top of another red block and no blue block stands on the top of another blue blocks. So our ideal tower would be something like this one, where we have a red block, then blue, then red, then blue. Or the other way could have been blue, red, and so on. Okay, we want both our towers to look like this. Okay, either blue, red, or red, blue. Okay, the operation that we can do is take the topmost element of one tower, shift it to the other tower. Okay, alright, so you have to check if it is possible to perform any number of operations to make the pair of towers beautiful. Alright, so the first line contains one integer, which is t. Okay, then in the rest of the input we have n and m, and then the entire towers. So if you look at the very first example, we have two towers. One is this of size 4 and one is this of size 3. And now if you see, what do we have? B, R, B, B. So we have B, B, R, R. And in the other one we have red, blue, red. Alright, so as you can see in this one, okay, in this one, this is already sorted in the terms of red, blue, and this is also sorted. So both of these are already beautiful, therefore the answer is yes. Similarly, for the next one, let's look at the next one. What do we have? We had what? B, R, B, R. And in the next one, we had what is R, R, B. What is next? R, R, B, R, B, R, B. Okay, this is the second input. Okay, so if you see, this is already beautiful because blue, red, blue, red. This is not beautiful. The other one is not beautiful. Why? Because we have two R's here. What we can do is take one from here and put it here. Okay, so if you see, basically we had what? B, R, B, R. The other input was R, R, B, R, B, R, B. Okay, what you can do is first take this blue and put it what? Here. Now take this red and put it here. So red goes here, you remove it from here. Then take this blue, put it here. Sorry. Put it here. Then take this red, put it here. Then again take this blue, put it on top, and then again take this red, put it here. Now if you see, this is beautiful and this is also beautiful. And that is what we need to see. Okay, so again, answer for this is yes. For the last one, the answer is no. Let's see why no. Okay, so if you see, we have what? B, R, B, R, R. And we have what? B, R, B, R. Now if you see, first one is not beautiful because it has two R's. Okay, but this is beautiful. Which means we need to take this R and place it somewhere else. But if we take this R and place it on the next one, this becomes non-beautiful. Therefore, there is no way to make both the tasks beautiful. And that's it. Okay. Now, how do we really solve this problem? Okay. Let me show you how. Okay. So, what we had was, we had two tars. This one and this one. Let's say this had blue, red, blue, red. This had blue, red, blue, blue. And let's say red, blue. Can we make these two tars beautiful? Yes, we can. How? We will shift some values from here to here. So we'll take this blue, put it here. We'll take this red, put it here. Then we'll take this blue, put it here. Okay. Now if you see, this is also beautiful, this is also beautiful. What we did was, we saw that this is beautiful because of this part. So we separated this. And that is all you have to do. Basically, if you see, you had one tar like this and one tar like this, let's say. This is bottom, this is bottom of both, and this is top. Okay, you can take either this operation or this operation. Okay, so what you can do is first see which either of these stars is not beautiful, because one will be beautiful, the other one won't be beautiful. If both of them are beautiful, non-beautiful, then you can just say that the answer is no, because you cannot make both beautiful in one go. You can only make one beautiful. Okay, now let's say this tower was not beautiful because of this part. Here you had two values and both were R, which means you have to take this part, put it here, and then see if this is beautiful and the rest of this is beautiful. The easier way of doing would be, if this was your first block, let's say this was front and this was rear, what you can do is, this was your other one, front and rear. Take this entire block, reverse it and put it here. This is rear, this is front. Because if you take the last element, this will go here only. So you just took the entire tar and reversed it and placed it on the other one. Now if you see, you have to just check if the this entire tar is beautiful. If it is beautiful, answer is yes, otherwise it is no. Because you've ensured that you need to check if there is only one point where the tar is not beautiful. Okay, because wherever, let's say if it was not beautiful at this point, you can take this part as one tar and remaining tar as the other tar. So basically what we did was, this was one tar, this was second tar. this is bottom, this is top, this is bottom, this is top. We took this star, reversed it and placed it on top. So this is top of the second one and this is bottom of the first one. Okay, now you have to check for the entire. So this is the entire tower. Now you just need to see if there is only one position because of which this is not beautiful. Only one position where you either have blue blue or red red. Okay, if there is one position, you can break it from that point. This tower will be tower 2, this tower will be tower 1. Okay, if none of these tower, like none of the position is not beautiful, okay, like if everything is beautiful, then answer is yes, obviously, because you can break it from anywhere. Okay, okay. If it is not beautiful because of one point, then you can separate it and again make it beautiful. But if it is not beautiful because of 2 points, okay, then the answer is no, because we only can distribute it into 2 towers. That's it. All right, so that is the entire thing you have to do for problem A. Let me just show the code. Some people are commenting that why is he spending so much time on A problem? The reason I'm spending so much time on problem A is because I'll tell you. If you see, I actually submitted my very first submission and got it wrong, and I submitted after 15 minutes because I started thinking something else. Okay, so I'm pretty sure there are other people as well who also started thinking something else, and because of which they took a lot of time, and maybe even after that they got it wrong or maybe got something else. Okay, this is the best explanation I think I can give you, and the easiest code as well. So as you can see, what I'm actually doing is, in this code, I had one tar, I named it NS. I had another tar, I named it MS. Then I reversed this tar. If this was bottom, this was top. I reversed this tar, this became top, this became bottom. This is my second tar. Then I placed it on this. So now I have tower this and blue. This is my MS tar. Now I have one tar, entire tar. In this tar, I just need to see if there are any one point where S of I is equals to S of I minus 1. If that is the case, that means we need to split it from that position. I'm just counting all the positions where this condition is true. If count is less than 2, that means I can either break it or these are already beautiful. If it is greater than 2, then the answer is no. That's it. That is all you had to do for this problem. Alright, so I'm pretty sure almost everyone was able to do this problem. So let's not waste any more time. I've already taken too much time in this one. And let's move to problem B. Alright, so idle point. You're given in one-dimensional segments. Each segment is denoted by 2 integers, its endpoint. Let's denote the function. Define the function fx as the number of segments covering point x, where L is the left endpoint and R is the right endpoint of the segment. So basically you have n segments. Okay, this is the left one, this is the right one. You have a point x. F of x is actually equals to the number of segments it is a part of. For example, oh come on. For example, let's say you had this as a line and you had this as a line. Okay, so if you see, there is one point here and one point here. These 2 points are actually occurring twice in one segment and one time in one segment. Therefore, count of both these points is 2. Okay, now an integer x is called idle if it belongs to more segments than any other integer point. So if let's say we had a number line. Okay, we had one number line. 1, 2, 3, 4, 5, 6, 7. Okay, let's say we had one segment from 2 to 4 and another segment from 3 to 5. Now, if you see, occurrence of 3 is 2 and occurrences of 4 is also 2, because 3 is occurring in this point also, line also, and in this line also, and 4 is also occurring in this one and this one. Therefore, neither 3 or 4 is idle. Okay. If we introduce one more line from here to, let's say, here. Now, if you see, count of 4 actually becomes 3. And 4 is an idle point. So, you're given an integer k. Your task is to determine whether it is possible to remove some, possibly 0 segments, so that the given point k becomes idle. Okay. So, let's look at the very first example only. So, if you look at the very first example, We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So here n is 4, k is 3. Okay. We have a segment from 1 to 3. Then we have a segment from 7 to 9. 7 to 9. We have a segment from 2 to 5. 2 to 5. And then we have a segment from 3 to 6. 3 to 6. Okay. Now if you see, 3 is actually present in 1 line, 2 line, 3 lines. 3, the occurrence of 3 is thrice. And there is no other point which is actually occurring thrice. Therefore, 3 already is an idle point. Answer of this is yes. Okay. Let's take the last example. In this one, if you see, I'll remove these. Okay. In this one, if you see, okay, we had what? Our n is 3, k is 5. We have a segment from 1 to 4. We have a segment from 6 to 7. 6 to 7. And we have a segment from 5 to 5, which is this point only. Am I missing something? Okay, we had a segment from... I am missing something. 3 to 5 is also a segment. 3 to 5 is also a segment. I am getting confused actually. So we have a segment. 3 is the number of point. K is this. 1 to 4. 6 to 7. 5 to 5. Okay, yeah, sorry. This is right actually. Okay. Now if you see, we need to make sure that 5 is an idle point. Right now, occurrence of 5 is 1, but occurrence of 6 is also 1, 7 is also 1. What we can do is, we can remove this segment and this segment. After that, only this segment will be left and occurrence of 5 will be 1. Occurrence of no other point will be 1. That's why 5 will become an idle point. Okay. Now, I'll not explain the no parts. Okay, the inputs where the answer is no. I'll just tell you the logic, like what you have to do. If you see, you have n number of segments, okay, and you need to ensure there is only one point which is k, okay, which is an idle point. The condition for becoming one point to be an idle point is that it has to be present in most of the segments, in the maximum number of segments, and there has to be no other point which is present. And we are allowed to remove any number of segments. So let's say we had a point x and it was present in some number of segments. So it is obvious that we have to remove all the remaining segments. Now we need to ensure that all the remaining segments don't have any other point whose occurrence is greater than x. Okay, to do that, what we can actually do is, if you see, let's say this is one segment. Okay, it had 4 points. We had another segment from here to here. Now, if you see, occurrence of this point is twice, occurrence of this point is also twice. This is something we do not want because now we have 2 points which are idle, but we only need 1 point which has to be k. So what you need to do is, you need to figure out any two segments which are like this and this. Now if you see, occurrence of this point is twice and occurrence of all the other points is 1. And we need to make sure that this point is k. So all you have to do is find out if there are any two segments, okay, any two segments in which k is a starting point and an ending point. That's it. Okay, because either this case or another case will be there is only one segment which starts from k and ends at k. So what you have to do is, for all the n number of segments that you have, make a map or set, any set. Okay, in this you have starting points, and then in another map you have all the ending points. Now you just need to see if this k is present in starting also and ending also. If k is present in starting and ending, that means either we had two segments, one segment had an ending point as k and another segment had a starting point as k, or we had only one segment whose starting was also k and ending was also k. In either case, the answer will be that particular segment or those two segments, and the answer will be yes. So that is all you have to check. Make a set of starting points and ending points. Okay, then after inserting all the starting and ending points, just check if k is present in both starting and ending sets. If it is present in both of them, that means the answer is yes, otherwise the answer is no. Okay, I hope this is also clear to everyone. Okay, again, pretty simple question. Actually easier than problem A, I would say, at least for me. And let me show you the code as well. Okay, hey, go to doc channel for great explanation. DCC channel. I don't know which channel that is. Pronoun, no, no. Okay. A says you're running some community for mentorship. No, I'm not really running any community right now. Okay, another approach, check consecutive color and check tops of tires. Okay. Okay, so this is the code. Okay, again, pretty simple problem. Okay, all I'm actually doing is I've taken all the starting points, pushed it into a set of S, and all the ending points, pushed it into a set of E. Then I'm just checking if K is present in the starting map and K is present in the ending set. If it is present in both, my flag is 1. If flag is 1, see out yes, otherwise no. That's it. That's all you had to do. Alright, so I hope this is also clear to everyone, and we can move forward to problem C, which I think is the whole reason many people are here. So, okay. How many people are actually here for problem C? Because I think most of you are here for problem C. I maintained a count of the segment in which beginning is K and ending is K, and if beginning and ending both are more than 1, then yes, otherwise no. Yeah, actually that is a better way of doing it because you're not really using any space for making two sets. So yeah, I think I should have also done this. Okay, many people actually said +1 I am because they are here for problem C, which is a very good problem. Okay, I'm actually going to teach you two different concepts in problem C. I'm here because I really don't understand the statement. Okay, I'm here to learn something new. Okay, I'm pretty sure Pragnesh, you are going to learn something new. Okay, so let me first read out the statement, explain the entire statement, give one example how it is working, and then I'll tell you the logic. Okay, cool. Alright, so a tea manufacturer decided to conduct a massive tea tasting. N sorts of tea will be tasted by N tasters. So we have 5 teas and 5 tasters. Now both the sorts of tea and the tasters are numbered from 1 to N. The manufacturer prepared AI milliliters of the ith sort of tea. So we had N number of teas, N number of tasters. Ith tea actually had AI quantity of tea. Okay, now the jth taster can drink bj milliliters of tea at once. Ith taster can actually drink only bj milliliters of tea in one go. Okay, the tasting will be conducted in steps. During the first step, the ith taster tastes the ith sort of tea. Basically, what we really have is, okay, let me go to this document. What we have is, we have n tasters, okay, and n teas. Okay, so let's make those. Right now, let's say we had first tea, second tea, third tea, fourth tea. Let's say we only had 4 teas. Okay, so these are tea, and then we have tasters. So we had first taster, second taster, third taster. In the starting turn, the tasting will be conducted in steps. During the first step, the ith taster tastes the ith sort of tea. Okay, so basically the ith taster, this is the ith taster right now. Sorry. This is the ith taster right now. The first taster will taste the very first tea. Second taster will taste the second tea. Third taster will taste the third tea, and so on. Okay. Now, then all tasters move to the previous sort of tea. Then during the second step, the ith taster moves to IA minus 1th sort of tea, and so on. Okay. So basically, if this was the entire tea set, let's say we had 3 tea sets. Okay. Or let's take this one only. I'm going to remove this. Right now, these all people are tasting. Come on. These all people are tasting. This person is tasting this one, this person is tasting this one, and this one. After one turn, what happens? Everything moves. The last taster, the first taster doesn't have anything to taste. The first taster doesn't have anything to taste. Second taster, so this was 1, 2, 3, and 4. Second taster tastes tea number 1. Third taster tastes tea number 2. Fourth taster tastes tea number 3, and so on. Okay. Then again in the next step, what happens? Everything moves. It becomes like this. The third taster, which is this one, third taster tastes tea number 1. The fourth taster tastes tea number 2. And this cycle keeps on going on till the end. Okay, let's get back to the equation. During the third step, and so on, so on. Then all tasters move through the previous sort of tea. Thus, during the second step, the ith taster tastes the I minus 1 sort of tea. The ith taster drinks minimum of AI minus 1 comma BI. Okay, so basically, ith tea had AI quantities. Okay, now BI can only, ith taster can only drink BI liters of tea. Now, whichever is minimum, that much amount will be taken by ith taster. And the remaining will be left there only for the next person to come in. Okay, that is the entire problem. We need to find out how much milliliters of tea did the very first person take, how much milliliters of tea did second taster take, and so on. That is the entire problem. So let me take the very first input and try to explain you what is happening here. So what is the first input? The first input is 10, 20, 50. So we have what? Okay, something is wrong. Yeah. Okay, so we have 10, 20, and what was the previous one? 10, 20, 15. Okay, then we had 9, 8, and 6. 9, 8, and 6. Okay, these are teas and these are tasters. Okay, so in the very first day, on the very first day, okay, so I'm actually writing these 1, 2, and 3. This one actually tells me how much tea did the very first person take, how much tea did the second person take, and how much tea did the third person take. Now, on the very first day, okay, first day, this first taster will actually taste 9 milliliters. Because at max, it can take 9 milliliters only, although 10 was present. Okay, this person will take 8 milliliters and this person will take 6 milliliters. Okay, now let me develop this. Now everything, okay, before that, how much is left? Only 1 milliliter is left, 12 milliliter is left now, and what? 9 milliliters is left now. Okay, now everything moves. All these people move. Okay, they move like this. Now, person number 2 will drink tea number 1. Only one was left. Only one was left. So this person will drink one amount of tea. Sorry, one amount of tea from here. Sorry. It might get a little confusing, but please try to bear with me. Okay. So, and this person, third person will actually drink 6 liters. 6 milliliters. Now again everything moves. Okay, before that, how much is left? This is 0 left because 8 we had to take, but one it gave to number second person only, so 0 left. Here 12 minus 6 is 6. Here the entire 9 is left. Now again everything moves. We had this and this moved. So this moved like this. Okay, since we had 0 amount of tea left here, it drank 0 tea on the last day. Okay, now if you sum these 9, 9 and 12. So person 1 drank 9 milliliters, person 2 drank 9 milliliters, person 3 drank 12 milliliters. And if you see, that is the answer. For the very first input, you will see that is the answer, 9, 9 and 12. Okay, so how do we really solve this? I'll take one more example. iPad and live stream has lag. iPad and live stream has lag. Like, are you saying iPad is moving slower than my video or what? Okay. Okay, good. Let me take one good example and I'll explain you further. So let's take one good example. Let me say this is T. Here I have tasters. Okay, so T is, let's say, 7, 6, 10, 5, 8, and I had 1, 2, 3, 4, 5. So taster 1 can drink one tea only. Taster 2 can drink 2, then 3, then 4 and 5. These are the teas I have. Okay, let me also write the sequence numbers for these. So basically this is 1, this is 2, this is 3, this is 4. These are the indexes. I'm taking everything. Okay, I'm taking everything as one based indexing. Okay, we'll remove zero based indexing because it is easier in these kind of questions. Okay, I'm taking everything as one based indexing. Now, if you see, again, I will say how much tea did first person take, how much tea did second person take, how much tea did third person take, how much tea did fourth person take, and how much tea did sixth person take. Okay, now on the first day, this person will actually drink 1 cup of tea. Okay, and how much is left now? Only 1 cup, 6 is left. Now let's look for person number 2. Person number 2 will drink 2 milliliters on day 1. Then it will move to the left. How much will this value drink from this? We have 6 left, so 6, minimum of 6 and 2 is 2, so it will drink 2 and then it will leave the party. Okay, and how much is left here? 4 is left here. Here also 4 is left because 6 minus 2 is 4. Now let's come on to the third person. It can drink 3 milliliters, okay, on any day at max. So on day 1, it will drink 3 milliliters because minimum of 10 and 3 is 3. Then it will move to the left, come on to this 6. It will say that, okay, 4 is left out of this, okay, and I can only drink 3, so I will drink 3. Again, it will move on the left. 4 is left, 3 I can maximum take, so I'll take 3. How much is remaining? Only 1 is remaining now. Here also only 1 is remaining now, and out of 10, only 7 is remaining. Okay, again coming on to the fourth person, it will say I can drink 4 milliliters on day 1. After this, 1 will be left. On day 2, I will move to the left and see, okay, 7 is left out of this 10. So I will drink 4 again. I'll drink 4 again. Yeah, I'll drink 4 again. How much will be left after this? 3 will be left. Again, I'll move on to the left part. Okay, I will say, okay, 1 was left. I can drink 4, so I need to drink 1 from here. So it will drink 1 and 0 will be left. Then again, I'll move left. 1 will be left. I can take 4. I will drink 1 only and 0 will be left here. And for the last person, it will say I can drink 5 on day 1. So it will drink 5 on day 1. Then it will move on to the left. Only 1 is left. So it will drink 1. Then again on the left, it will drink 3. And then everything is 0. Sorry, this is left for 3. But there is no other person to drink that tea. So this 3 will be left only. How much did the very first person take? 1. The second person took what? 4. The third person took 9. Fourth person took what? 10. And this person took 9. That is the answer for this one. Okay. Now, how do we understand this? Okay. How do we really find this? Let's try to, instead of trying to find like how many tea did ith taster drink, let's try to find how evenly was the ith tea distributed. So if I have like X milliliters of tea for the ith at the ith index, who all tasters actually drank it? Okay. So let me explain that. If you see this 7, if you look at this 7, who all drank from this 7? Person 1 drank, person 2 also drank, and person 3 also drank. Now, who all drank from this 6? From this 6, person 2 drank, person 3 drank, and person 4 also drank. Who all drank from this 10? This person drank, and this person also drank. Who all drank from this 5? Okay, this person drank and the next person also drank. And who all drank from the last one, which is this one? Only this person. So as you can see, for the ith T, that person and the people after that are able to drink. But at some point, if you look at the very first T, if you look at the very first T, if you look at the very first T, it was only able to be used by the third person only. After that, we could not use it. Sorry, it was used till the fourth person, I think. Yeah, it was used till the fourth person. Till here. Okay, after that, we could not use it. So we had a break here. For second person, we were able to use it till again the fourth person. For third person, we were able to use it till the fifth person and so on. Okay. Now, how do we really find this? If you see, this 7 is nothing but 1 plus 2 plus 3 plus some part of this 4. And that is why it was able to drink till fourth person. So, if you have a prefix array, let's say this is 1, this is what? 3, this is what? 6, and then this is 10. You will be able to, by using lower bound, you will be able to find out, okay, that this person can only drink till this index only. Okay, this person is sorted. We are able to figure out till which index it is able to drink. How much it is able to drink, that I'll tell you again. Okay, but it is able to drink till this point. Okay, for the second person, this 6, we know that, okay, now we cannot really use this prefix array because it is prefixed from this one. So every index after this has this 1 in it. What we can do is we can add this 1 to this 6 only. So instead of checking for this 6, we can add the previous value, which is this 1, and check for 7. If we check for this 7 in all the prefix array, we will be able to figure out again that, okay, by lower bound, what is lower bound? Lower bound actually takes me to an index which is like whose value is either greater than or equal to that particular value. Okay, so this 7 will again take me to the fourth person, saying that second person will be able to reach till fourth person only. Again, if we move forward for the third person, it will say I have a value of 10. But I cannot use this prefix array because it actually contains all the previous values as well. But we know that this value is nothing but summation of all the previous value. So we'll add this 3 to this 10. So we have 10 plus 3. We had what? 10 plus 3, which is nothing but 13. We will make a lower bound for 13. This is what? 15. Okay. When we do a lower bound for 13, we will come on to this index, meaning that the third person will be able to reach till the last person. And that is how we will be able to find out which T will reach which index. Okay. So what now? We had these T's, these are T's, and these are tasters. Okay, we know if this is okay. Okay, now we know that if this is the ith index, using the above theorem, okay, using the above logic, we are able to figure out how many people are actually able to drink this ith T. Okay, so how we are actually able to do this? We first have a prefix array. Okay, let me just take these values only. We had what? 5, 6, 10, 5, 8. 5. We had 5, 6, 10, 5, 8. Okay, let me just remove the extra. Let me make a new one only. We have 5, 6, 10, 5, 8. These are T. Okay, and then for tasters, first person can take 1, second can take 2, 3, 4, and 5. This is just some random values I have taken in order. Okay, for now. Now, let's try to figure out till what index this 6 will move. Before that, let's make a prefix array, or let's try to figure out till what index this 10 will move. Before that, let's make a prefix one. These are tasters, and this is nothing but prefix underscore tasters. Okay, so this will be 1, this will be 3, this will be what, 6, this will be 10, and this will be 15. Now, if you see this 10, we have to find the lower bound for this 10 in this tasters. Okay, But we cannot really do that in the prefix array because we know that till this point we have taken the summation of all these values. So what we do is we say that since we know that, okay, if you try to see all of these as building, okay, let's say this is building 1 of size 1, this is building 2 of size 3, then this is building 3 of size 6, this is building of size 10. If you see, everything is actually moving after this 3. If you remove this 3 from everything, you will get the original value. You will get this 3. Okay. For the next one, this is 6. If you remove the 6 from 10, you will get 4. Okay. So what I'm trying to say is, sorry. Okay. What I am trying to say is that this 10, to find till which index this 10 will go, you first take the summation of all the previous values, which is nothing but prefix of I minus 1. You add it to this 3. So your value that you have to check becomes A of I plus prefix of I minus 1. This value is something which you need to see in this prefix array, will tell you till which index this T will move. So when you actually see AI is 10, prefix is 3, this gives you 13. When you try to figure out the lower bound of 13, you will come on to this 15. Which means you are able to move till 5th person. But for the last person, since we know we have taken lower bound, it is either equal to or greater. So the last person was able to take some part of it. Okay, how much part that we can figure out? This is 13. Okay, this is 10. The previous value is 10. So this person was able to take 3 values from it, which is nothing but like 15 minus 13, which is 2, sorry, was able to drink only 2. And if you see the last person was able to drink, we are actually on this 10, which is nothing but, okay, I'm getting confused. Okay, the last person, the last person was able to drink T of value 2 from this one. How 2? It has to be 3, 7, 6 and 10. Oh, sorry. We had 13. 13 minus 10 is 3. So 3. And as you can see in this table also, third person was able to drink a value of 3. Okay. So that is how you can actually find it. All the values before it, they will take their entire value. Okay. How many people are actually able to follow this? I think I have even confused you. This is a little trickier problem to like explain. I just want to know like how many people are actually able to understand. If not many people are able to understand, I'll just explain it very fastly in a more neat manner. No clue, confused. Okay. Okay. Let me just try to help you understand this again. Okay. So Yagnik says can follow. Really nice. Can you explain minus part? Okay, I'll explain minus part. Confusion. Okay, cool. So let's say we had this T. These are T's. We are at some ith index. We need to figure out if these are tasters. These are tasters. Okay. We need to figure out till which index this T will be passed on. Okay. Because we know that tasters are moving on the left direction. So these are moving in the left direction. So this T will actually move in the right direction in a way. We need to figure out till which index this ith T will be passed on. Okay. Now, what we are actually doing is, before that we are actually finding a prefix array. Prefix array of all these tasters. So we have a prefix array of all these tasters. Okay. Ideally, let's say this is AI, BI, this is BI plus 1, BI plus 2, and so on. Ideally, brute force approach would be, if this is AI, you will see that till which place, like if BI plus BI plus 1 plus BI plus 2 is lesser than AI. If that is the case, we are able to move till this one, and then again we move forward. So basically for this, first we see if AI is greater than BI. If yes, ith will be done. Then we move on to what I plus 1, but we know that ai is not entirely now ai minus b of I if it is greater than b of I plus 1. If that is the case, we are able to consume I plus 1th person also. If ai minus bi plus 1 is greater than bi plus 2, then we are able to consume I plus 2 also. That is the brute force way. What better way could be if we say like we update bi b of I plus 1 to be b of I plus b of I plus 1. B of I remains bi only. B of I plus 2 becomes b of I plus b of I plus 1 plus b of I plus 2. This is nothing but prefixes. These are prefixes. Now, if ai is greater than bi, that means I am able to consume the ith t. If ai is greater than bi plus 1, I am able to consume the I plus 1th t. And if ai is greater than bi plus 1 plus bi plus 2, then I am able to consume the ith plus 2 t as well. But when we are finding the prefix array, this bi will be b1 plus b2 plus b3 till bi. This b2, so basically bi will be b1 plus b2 plus b3 so on till bi. B of I plus 1 will be, sorry, let's say this p. Okay, p1 is prefix 1. Prefix I plus 1. Prefix I plus 1 will be b1 plus b2 so on till b of I plus 1 and so on. But we only needed bi plus 1, bi plus 1, bi plus 2 and so on. What we do is we actually, instead of decreasing all these values, instead of decreasing all these prefixes by the summation of bi minus 1, what we do is we add bi minus 1 to ai. Okay, so basically what we are actually doing is, let's say I had this, I had this, I had this, and I had to see if, like, let's say I had some other value. This is ai. I had to see this ai is greater than which one, smaller than which one. One way would be I compare it with this one, I compare it with this one, compare it with this one. The other way would be I remove these values from all. That is what I'm actually doing. I am removing all this value and adding it to this ai, and then finding my prefix, like lower bound for all the remaining values. When I do that, I will get to know that, okay, I'm able to reach till I plus 2. Okay, which means I will take some value from I plus 2 and till bi plus 1, everything will get their entire quantity. Okay, I hope some of this is clear to you now. Again, like, pretty confusing. Even I am trying to think of a way like with which I can actually explain you better, but I think this is the best I can do. Nirmal says got. Okay, now again, so you had, these are t's, this is the ith person. Okay, you are somehow able to figure out for all the tasters that you are able to reach till this point for the ith t, which means this index will take some value and all the remaining index from here to here will take their entire quantity. So this will take like bi, this will take bi plus 1, this will take bi plus 2. But this might not be b of I plus 3, because it might be that your remaining value for the ith t was lesser than bi plus 3. So you will take that remaining value only for this one. Okay, Yagni says I read your code and was able to understand the lower bound, but not further. Yeah, I'll explain the further part. I'm actually explaining the further part now. So what you can actually say is that this person, this chaser will get their entire bi value. This person will also get their entire bi plus 1 value. This person will also get their entire bi plus 2 value. Now, if we try to generalize this, okay, let's try to generalize this. We had 5 indexes. Okay, this is T, this is tasters. Okay, for the first person, let's say the first person is able to reach till here. Okay. Means it will take the entire B1. Okay, it could take entire B2 as well. It could take entire B2 as well, but let's say this value A1 was lesser than B1 plus B2. So it was only able to take some X value. Okay. What you do is, with this we know that it was able to take the entire value of B1, okay, and some value from B2. Let's make two arrays now, times, okay, and what? Add. Again, 5 indexes for these. I know I'm able to take the entire B1 value, okay, and what? A1 minus B1 value from the second person. Like the second person is able to take AI minus B1 value, which is X, but the first person was able to take the entire B1 value. Let's come on to the next person. Let's come on to A2. Let's say A2 was able to take till this value, fourth value, which means it was able to take the entire B2 value. It was able to take the entire B3 value and some part of B4. How we can say is like what? A1 minus B2 minus B3. Okay, fourth person was able to drink this amount of tea from A2. Got it? Now, moving on to the third person. Let's say this person was only able to drink till fourth person only again, which means it was B3 was able to take the entire value. So again, one more B3. But from B4, like fourth person was able to take only some value of it. This is A2. Okay, which is A3 minus B3. This much amount only B4 was like the fourth person was able to take. Okay. After that, if you find the summation of like this value, 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 you will be find like the first person was able to drink this much tea, second person was able to drink this much tea, third person was able to drink this much tea. We still have one more optimization to do here. If you see, okay, this optimization is actually known as partial sum. This is a technique known as partial sum. I'll explain this partial sum technique. Okay, let's say you have an entire array and you have to increment all the values from, okay, let's say this is one large array and you have to increment all the values from this index to this index. Then someone comes in and says you have to increment all the values from this index to this index. How will you really do that? One way is you first increment, like mark all the values as like 1, 1, 1, 1, 1, 1, 1. Then when the second person comes in, you make another one. So you make this one as 2 basically, this one as 2, this one as 2, and this person as 2. One other way of doing this is you mark this index as 1 and the index before this as minus 1, this as minus 1. Similarly, you mark this index as 1 and you mark this index as the index before this as minus 1. Now your array becomes, let's say you have minus 1 here, then after moving forward you have 1 here, and after moving forward, let's say you have 1 here. Now if you try to find the prefix of this in the opposite direction, you will say, let me mark this with yellow. So this is 1, this is 1, this is minus 1, this is minus 1. Now if you try to figure out the prefix of this, it will come out to be 1, 1, 1. Now 1 is added. This becomes 2, 2, 2, 2. Now 1 is decremented 1. Okay. Again 1. Now 1 is also decremented 0. And this is what we did. We first incremented from here till what? Here. And then we incremented from here till here. This technique is called partial sum. Okay. Like if this is L, this is R, you first add 1 to index of R and then you decrement 1 from index of L minus 1. After doing all the operations, you move from the backward direction and find the prefix sum. That will give you the final array. That is the same thing we have to do here. If for the very first person, we knew we are able to take it till the third index, that means for index 1 and 2, it will be the same. Okay, so what we can do is in the times array, we can mark index 2 as 1 and index 0, let's say this is 0, as -1. For person 2, let's say it is able to go from second till fourth. So what we will do is again put 1 for the fourth person and then -1 for the first person, because it was able to go from second to fourth. Okay, then for the third person, it was able to go from third to fourth only. So again, add 1 to fourth index and then -1 to second index. So this array, if you see, actually became, this is 0, 1, 2, 3, 4. This is -1, this is -1. Second became what? 1 minus 1 is 0. And this became what? 2. So your final answer becomes 2, 2, 2, -1 is 1, 0. That means BI was consumed one time, B2 was consumed twice, B3 was consumed twice, and B4 was consumed twice. This is known as partial sum. So that is the entire logic. I honestly don't know like how many people were able to understand this. A pretty lengthy problem, I would say, for problem C. But let me show the code and again like try to help you understand some part of it, from where we can learn all these tricky techniques, from giving context, learning new approaches. That is how, like, I also got to know about partial sum from one of Ericto's stream. I think I was watching Ericto's stream and then he told me, like, for a question, he told me like how Ericto's stream, like how partial sum works. And that is how I learned it. And then like after that, I've taught to so many people. Like this partial sum technique is something that not many people know, but it is a very neat and small trick which can be applied many places. Okay. Let me quickly try to understand, like help you understand the code. Okay. This is my array AI. This is my array BI. This is T. This is tasters. Okay. Then I'm finding the prefix of all the tasters. So this is my prefix array. Okay. After that, I'm just making two arrays, add and times. Add is actually containing the last index till which ith index was able to go on and how much value was this last index able to consume from the ith t. I'll again repeat. Add array is actually containing how much t this index is able to consume from the ith index. Okay. Times is nothing but how many times this ith index is being consumed. That's it. So then this is the main part. Here what I'm actually doing is, if I have this is t, again this is tasters, and if this is prefix, for this ith index, what I'm actually doing is, I first take this ai, add prefix of I minus 1, add prefix of I minus 1 to it. My value becomes ai plus prefix of I minus 1, ai plus prefix of I minus 1. Then I try to find the lower bound in the prefix array. Let's say it was able to reach till this index. I see if this index is less than equals to n. If it is greater than n, that means I was able, like all the remaining people were able to consume from the ith t. Okay. But if it is less than n, then I have my times array here and my add array here. Okay. In my times array, till index I minus 1, if I was able to reach till this point, till 1 minus 1th index, I say plus 1, and then from I minus 1, for I minus 1, I actually say minus 1. Okay, this is times, and this is add. Okay, and for add index, for this particular index in add, I just put down the remaining value that I might be left with after consuming all these t's. How I am actually finding this? I know the summation of this value, like summation of all the t's till this point. This is nothing but prefix of this point, this value. I know that this a of I actually contained this value as well. If I subtract these two values, like this value from these two values, I will get the summation of these values. Okay, the difference of this value minus this value is something I will have for this particular index. That I will store here. that is add of index I. Minimum value of value minus prefix of I minus 1. Okay, I didn't really have to write minimum. I could actually write this part only. I know like it will be this only. Okay, but now since it is like less than equal to m for the last index, it might be wrong. So you need to minimum. Okay, so value, your value was a of I. Your value was a of I plus prefix of I minus 1. Okay, so this is nothing but a of I plus prefix of I minus 1 minus prefix of index. Prefix of index. Prefix of index is this entire array. Okay, P of I minus 1 is this part. So this subtraction actually gives me this array, and then removing this AI actually tells me out of this array how much value will be consumed by all these. Okay, that amount of value will be taken for the last person, that is add of index. Okay, then like in the end, I'm just looking at the count, which is nothing, like I'm again going in the backwards direction for the times array, adding their count, multiplying their count with BIs, adding it for the ith person, and again adding the add array for the ith person, and that's it. After that, I print my answer. So that is the entire logic for problem C. Okay, a pretty complex problem, I would say. I now feel like it might have been problem D. Okay, I'm not sure, like maybe there is a better better way to do it. I don't think there's a better way to do it, although I think this is the approach. Okay, it is really hard to explain this approach, but I hope I did my best and you're able to understand it now. If not, maybe you can try going back and then trying to understand it. Okay, I think we should move on to problem D, which is a very easy problem. I will be done with it in like 5-10 minutes only. So let's start with problem D now. Okay. Let's move to problem D. Okay. So the question says that you are given an undirected graph containing n vertices and n edges. We have n vertices and n edges. Never says didn't even try D. Maybe like this is something I used to do. I used to start reading the question and I would see that, okay, this is a graph problem. I don't know how to solve graphs and I would just leave it. But I'm telling you, in 50% of the question, 0% graph knowledge is required. Like in this question, you really need 0% knowledge of graphs to find the solution for this problem. So always read the statement, try that problem, and then see like maybe like you are able to understand it and like are able to find the solution even without any knowledge. Okay, so you're given an undirected graph containing n vertices and n edges where n is divisible by 6. Each edge has a weight which is a positive integer. Okay, now the graph has the following structure. It is split into n by 3 triplets. The first triplet contains vertices 1, 2, 3, the second one 4, 5, 6, and so on. So basically you have n number of vertices. Okay, you've actually divided all these vertices into triplets. 1, 2, 3 is one triplet. Let's call these sets. 1, 2, 3 is one set, 4, 5, 6 is another set, 7, 8, 9 is another set, and so on. And we know that n is divisible by 6. Now, you have to paint the vertices of this graph into two colors, red and blue. Each vertex should have exactly one color. There should be exactly n by 2 red vertices and n by 2 blue vertices. The coloring is called valid if it meets the constraints. Okay, so let me not waste time and explain from the very first input only what they're trying to say. So basically what they're trying to say is that we had what? 12 vertices and 12 edges. Okay, these are the 12 vertices. We have what? 1, 2, 3, 4, 5, 6, and so on till 12. And 12 edges. Every triplet is connected inside. So basically 1, 2, and 3 are connected internally. 1 is connected to 2 and 3. 2 is connected to 1 and 3, and so on. Every triplet is connected to all the adjacent pairs. And no two triplets are connected by any edge. So we had 12 vertices, 12 edges like this. Okay. These are the weights which are given. You can just see from the input how the weights are given. We need to color the vertices by red and blue such that after coloring, if you see, Let W be the maximum possible weight of a valid coloring. How do we really define a valid coloring? The weight of the coloring is the sum of weights of edges containing two vertices with different colors. So basically what they are saying is, let's say we mark this with blue and then we marked these two nodes with red. What does this really mean? This means that this edge and this edge are connected two vertices of different colors. That means weight of this triplet is 3 plus 3, which is 6. Similarly, you need to find the weight of all the triplets such that number of red nodes is equal to number of blue nodes and summation of all the weights is maximum. Okay, now let that maximum weight be W. You need to find all the valid ways of coloring this graph such that the weight comes out to be W. Now, since all the triplets are independent, which means for every triplet we need to maximize its weight. We know that when we are counting weight, okay, we can at most take two edges only, because since it is a graph with 3 nodes, we cannot color the graph in such a way that all the 3 edges can be taken, because we only have 2 colors. Okay, if we color the very first node with blue, second node with red, for the third node we will either have to take red or blue, which means there will be one edge which will have same colors. Okay, so for this one we took these two. Okay. Now let me remove these all things. So let's look at every triplet now. Let's look at one triplet with 1, 2, 3. If you see for this triplet, if you look at the very first triplet, we have edges 3, 3 and 1. Since we have to maximize the weight, we need to take edge with weight 3 and 3. What are the possible ways of taking this? Either we can say this is red and this is blue and this is blue. Okay. Or we can say this is blue, this is red and this is red. There is no other way. Right? There is no other way of doing this. Okay. Which means basically, I'll just rub these again. Which means that if we had this triplet, the node with value 3, which had 2 common values, had to be colored with a different color. This is different, whereas these two are same. Okay. So there is one node which can be different. We cannot have one as a different node because then the edges will be different. Okay. So if you look at this triplet, there were 2 combinations. One with red, one with blue. Okay. Now let's look at this triplet. If you see in this triplet, all the values are different, 8, 7 and 5. Okay. Which means we need to take this edge and this edge because these are greater. In order to take this edge and this edge, we need to color this differently and this same and this also same. I can either have this 4 as blue, this as red, or I can have 4 as red and then 6 and 5 as blue. So again, there are 2 combinations. One for red, one for blue. Moving on to this triplet. If you see, all the values are 2, which means we can take any 2 edges. Which means I can either have 9 as different, this as same and same, or I can have 9 and 8 as same, these two are same, this as different, and so on. So basically, if you see, there are 3 nodes. So either 3 of the nodes can be taken as a different color, and that node can be taken either blue or red. So in total 6 combinations. How? 3 nodes with 2 colors. Basically, either you say, if you select 9 and say like I can either have 9 as red and then 7 and 8 will be blue, or 9 as blue, 7 and 8 will be red. These are 2 combinations with using 9. I can make 2 more combinations with 7, 2 more combinations with 8. So total 6 combinations. Similarly, for this one, if you see we have 2, 2 and 4, that means we have to take one edge with weight 4. Now we can either take this edge or this edge. And for this one, if you will see, there will be 4 combinations. One will be, you make this 10 as red, then this will be blue and blue. Okay. Other way would be, you make this red, this blue and this blue. Now you'll be taking this edge and this edge, or the reverse of this. When you mark this red and blue, you now say this is blue, this is red and red. And for this red, blue, you will say this is blue, this is red, this is red. So basically for this one, we had 4 combinations. So for this one, we had 4 combinations. For this one, we had 2 combinations. For this one, we had 2 combinations, and then 6 combinations. Okay. Now, every combination will be multiplied with each other because all of these are independent quantities. Okay. So if you see, there are many combinations which are duplicate. Okay. How? For one triplet, you are coloring one node as red and 2 as blue, or one node as blue and 2 as red. We know that we need n by 2 red nodes and n by 2 blue nodes. Okay. So a neater way of doing this will be, out of all the, let's say we had n by 4 triplets, n by 3 triplets, n by 3 triplets. Okay. What we did was, we said half of the triplets will have 1 blue and rest half will have 2 blue. Okay. So basically, let's say count triplets is n by 3. Okay. We will say half of these n by 3 will have blue for one node and half of these will have blue for 2 nodes. Which means, let's call this m. Of all these m triplets, we need MC m by 2. All the ways of finding m by 2 triplets in which I can have like those nodes with blue color. Rest I can have with red color. Okay, so MC m by 2 for that case, that I'm actually selecting half of the triplets in which I will have blue for one node and red for 2 nodes. Okay. Now, if you see, with this, you have already selected, like finalized the color, that I know which, like for this triplet, how many blue and how many red nodes am I actually going to take. Okay. Since I've already decided the colors, if you see for this particular triplet, there were two combinations in which I used 1 red and 2 blue, and 2 combinations in which I used 2 red and 1 blue. But since I've already decided like how my coloring is going to be, how many blues and reds I'm actually going to take, I can say that for this triplet, I only have 2 ways. Similarly, for the last triplet, okay, let me just remove these, delete screenshot. So what I can say is, for this, our answer was 4. Okay, but in this 4, we had 2 triplets for which I was taking 1 red and 2 blue nodes, and 2 triplets for which I was taking 2 red and 1 blue nodes. But I've already decided how many number of red nodes and blue nodes I need for this triplet. So I can say I will actually have 2 combinations from this triplet. Similarly, for this one, we had 6. Out of these 6, 3 had 1 blue, 2 red, and 3 had 2 blue, 3 red. Okay, 2 blue, 1 red. Okay, so from this also you only have 3 combinations. Similarly, from this we had 2 combinations in total, but they will come down to 1. And from this also we had 2 combinations in total, they will come down to 1. What you have to do is, from every kind of triplet, for all the triplets that you have to find out how many combinations they can give. This can give 1 combination, this can give 2 combinations, this can give 3 combinations, and this can give 1 combination. Multiply all these values. Okay, so let's say this gave me like what, x1, x2, x3, x4. Okay, so I multiplied x1, x2, x3, and x4. Then I multiplied this with MC m by 2, where my m was number of triplets. Okay, because by using MC m by 2, I am ensuring that I am choosing out of all the m triplets, m by 2 triplets, and let's say for those m by 2 triplets, I will say that okay, I'll have 1 blue node and 2 red nodes. Then, since I've already marked the colors, now I can say for every, like for a particular kind of coloring, how many ways do I have for this triplet to actually give me 2 maximum edges. Okay, so x1 for this triplet, x2 for this one, x3 for this one, and that is it. That is how you are going to find the entire answer. That is all you had to do. Okay, now like how do you really find x1, x2, x3? If you have all the edges same, then your answer will be 3 for that particular triplet. Okay. If you have all the edges different, then your answer will be 1. If two edges are same, one is different, then your answer might be 2 or 1 depending on the case. How? Okay, if the smaller value is occurring once and larger value is occurring twice, then only one way. If the smaller value is occurring twice and larger value is occurring once, then 2 ways. That's it. That is how you have to solve this problem. I'll quickly show my code. If I come to code, this is the entire code. So what I'm actually doing is I'm scanning the entire array, okay, marking all the like edges and everything. Okay, then for every triplet, what I'm actually doing is for every triplet I'm actually doing here. Okay, whenever I encounter a triplet, okay, whenever I encounter a triplet, I'm actually inserting it in my set. I'm inserting it in my set. Then when I have 3 values, okay, then I see if the size of set is equals to 3. If it is equals to 3, that means all the edges were different. That means I need to multiply it with my answer by 1 only, because there is only one way of finding two highest value edges. If it is equal to 2, that means one value is occurring twice and one value is occurring once. Now we need to see if the smaller value is occurring twice. If the smaller value is occurring twice, then I have 2 combinations. Okay. If the larger value is occurring twice, then I have 1 combination only. So I'm doing that only using count. Okay. S dot begin is actually the smaller value. If the count of smaller values twice, then 2 ways. If it is 1, then 1 way. Else will actually say that if my set size is 1, if it is equal to 1, that means all the edges are same. I can select any node and the number of ways is 3. I multiply all these values and then I find NCR. NCR for where n is m, which is nothing but number of triplets, and r is m by 2. I have a separate function for that, and then I just print the answer. This NCR is nothing but I'm actually, if you see, I'm using power function, which is here. This is actually matrix exponentiation. Okay. If you don't know about this, just Google matrix exponentiation for finding power. You will get a Geeks for Geeks link. Read it through that. And we are using that for finding power. As NCR. This is what? Matrix exponentiation. Okay. And then for finding NCR, I'm actually using Fermat's little theorem. Both of these you can actually like just read from Geek for Geeks. You will be able to understand like what these are. Okay, I actually have saved these codes somewhere so that it doesn't really take me much time to search for these codes. You can also do the same. Someday I'll also share all the files that I have for all the codes. Okay, but yeah, that is how you had to solve this problem. Okay, cool. I hope everybody was able to understand problem D. D is a very easy problem. Okay, you just have to know how to find NCR. That's it. Okay. Today's stream is extended. It is like 1 hour 26 minutes. Even I am tired up after this. Okay, rating of question C. I think rating of problem C should be somewhere around 1700. That 1700, 1800 at least. And for problem D, I think it should be like again 1700, 1800 only. Nothing much. Okay. Is there anything else anybody wants to ask? Else I can end the stream. Today's stream is really long because of problem C. I think I took more than 45 minutes for problem C. And even after that, I don't think I did very good in explaining. Okay. How to practice graph. I'll tell you how I did graph. Basically, like I first had to ensure that I need to get better at DFS and BFS because those are the building blocks of graph. Okay, so what I did was, I'm not sure if I'll be able to do it here. I just read how DFS and BFS work. I went to problem set. Then I picked my tag as graph, sorted all these on the number of submissions, and then I completed all the problems of page 1 and page 2. If you see page 1 and page 2, I've completed all the problems. Okay, these are all the new problems. That's why they are not green. But yeah, that after that, I was very sure about my DFS and BFS. I knew if there is any question which only requires DFS and BFS, I will be able to do it. After that, I read all these shortest path algorithms and everything else, but they are not very much used in competitive programming. They are only used for very good questions. For problems till problem D or E also, I would say only DFS and BFS are used. So if you're good at DFS and BFS, you are very easily like able to solve major of the graph problems, and that is how I did it. I did the same thing for DP as well, and that worked very good for me. Okay, all right. So is n to the power 2 valid for C? I am not n to the power 2. No, no, that is not valid. Any good source? I have already told about that. How? Thank you. How did you practice combinations? Actually, when I was preparing for ACM ICPC, I went to Geeks for Geeks. Okay, I went to Geeks for Geeks. I wish I could show you like Geeks for Geeks also here. I went to Geeks for Geeks. There is a section for maths. I read the entire section. That's all. Like I understood all the algorithms they have, not till the geometry and everything, but I did like more than 50% of it. Through that, I was able to like understand Chinese remainder theorem, matrix exponentiation, Fermat's-Little theorem, all these algorithms. Okay, I was able to understand from there, and then I applied them into the questions. Did you do lead code? No, honestly, I didn't really do lead code when I was in college. Even after college, also, I recently started doing lead code in the last 1 or 2 years. Like after I graduated. Before that, I had never done lead code. Even in interviews, like standard problems, I would used to struggle because I had never done lead code. I didn't really knew what standard problems were. But I did Geeks for Geeks. I solved many problems on Geeks for Geeks. I did many problems on Geeks for Geeks, but I never did lead code, which is something that I regret. I should have like did lead code very early. Okay, I'm really bad at permutations and combinations. Please suggest how to be thorough with it. Just go to Geeks for Geeks. Let me just try. Okay, let me just try to show you like how I did it. Geeks for Geeks has actually like revamped their interface, and it is difficult for me now. Earlier, I used to know like where everything is. No, this doesn't have algorithms. Mathematical, I think. Yeah, this one. Okay, so I did these entirely. Like I did all the problems of divisibility in large numbers. Then I did GCD LCM. Then I did series. Then I did number digits, algebra, number system. No. Yeah, I did factorial. I did modular arithmetic. I did prime factorization and divisors. Fibonacci numbers also. Okay, so yeah, NCR combinations. There are all the ways of actually finding NCR. I did all of these. Okay, and I can also share this as well if you want. Let me just open it. So basically, I have a file while I was learning about maths, like for CP. I actually made a file in which I actually wrote all the like codes I would ever need for maths. Let me just try to find it if I still have it. Oh, oh. I'm not able to find it actually. Okay, I'll show it in the next stream. I'm not able to really open it up on my iPad. Like I do have it, but I'm not able to show it on my iPad. Okay. So, is there anything else? C and D should have changed places in my opinion. Yeah, even I would agree with that. Like if like I actually did D before C. Actually, I saw like number of summations in C in D is less, but number of summations in C is also less. With that, I knew like C is easier. Any plans for development related content in future? I don't think so. Like I don't think I'm going to do development related content in the next 6 months. I am actually planning something with system design for the next 2-3 months. Where should I learn DP? You can do CACS. That is a very good problem set for DP. It actually contains all the 20 classical problems of DP. If you do those problems, you will get basic understanding of DP. Then for practice, just open problem set of Codeforces. That is how I did it. Okay, Yagnik says 2D. Again for 2D also, just go to CACS. Namal says thanks, Naman. Okay. Anything else? Since there are people watching the stream already, right now also, I'm just waiting for people to ask me questions. Otherwise, I can end the stream. Thanks, bro. I'm stuck at specialist. Please help how to reach expert. Practice. That's it. Like, I don't think I can say anything. Let's try to, like, since if you're a specialist, that means you need to get fast. That is the first thing that you need to do. And you need to ensure that you always solve problem C. Okay. To solve problem C, I've already told this to people. Just solve the ladder of problem C on A2OJ. I became pupil today from a specialist. Sad. No, is pupil above specialist or below? I don't remember. Any tips for clearing online assessment questions? Again, like for online assessment, like if you're good at CP, you don't really need to care about online assessment. Like I never had any problem in clearing any online assessment except for coordination. That was difficult. But yeah, for all others, like they're very easy if you're doing good at CP. Yeah, it's true. I solved C in a slow rate. Today, C, it is okay if you took time. Like even I took like 40 minutes. Okay, so it is okay if you took time for C. C is a very implementation centric problem with some good concepts. Okay. I had some, yeah, okay. Someone was asking how to become expert. In order to become expert, you always need to ensure that you are solving problem C. Even if it takes time, you need to solve problem ABC in every contest. For that, you need to start doing A2OJ. Do I have it here? Yeah, I have it here. So basically A2OJ used to be a website which was shut down later on by the author. So this random person actually made a web app for that, which is very good. Just let me open it. Sorry, we need to open for Div-2 C. So if you open for Div-2 C, you will actually get all these. So these are 100 problems actually, and these are very good problems. Okay, if you do all these 100 problems, it is for sure that you will be able to solve problem C in every contest. Okay, I did all these. I don't have many yeses here because I was actually solving these with a friend of mine while preparing for ACM ICPC. So we did all these problems, and because of these problems, I was always able to solve problem C after that. Okay, like these are very good problems with very good concepts. ABC speed courses and become expert. Yeah, you can become expert by like being very fast at ABC as well. Even like it's not even about C. When I became candidate master for the very first time, I only solved A and B. That's it. If I show you, like that is how speed forces work sometimes, not every time. Can I open this con? Oh, sorry. I hope everybody can see my screen. Yeah, they can. Why is it not going back? If I go to my profile, if you look at the very first contest through which I became expert, if you go to standings, where is it? There. If you go to standings, I only solved problem A and B. That's it. And I became a candidate master after that. Reason was because I solved problem B after A. And both A and B were very difficult in this contest. But since I solved problem B after A, like before A, I had many points. And because of that, I became candidate master. So yeah, sometimes speed forces does work, but not every time. Okay. Alright, I think we have stayed the stream for long enough. Let's end the stream. And I'll see you in the next contest. Not in the next contest, next to next contest. I won't be giving this 19th February contest, but I'll give this 25th February contest. Okay. So let's meet after that. Do give this stream a thumbs up if you liked it. And also subscribe to the channel. Tell it to your friends as well if they are also interested in getting better at CP and Codeforces. Yeah, that's it. Bye.